I have discussed two problems. Just I explained the procedure. Today we will solve both the problems. Means this second problem on deflection and one problem on flexural. Okay. We will solve both these two problems. Okay. All of you read the second problem. All of you read the second problem. Finished, students? Have you finished writing the problem? Okay. Just go through the problem. Estimate the deflection under service loads for the composite T beam of example 1 means previous problem. If the modulus of elasticity of concrete in the precast beam and cast in situ slab are 35 and 28 kilonewton per meter square respectively. All the data is same only, but in the previous problem a single modulus of elasticity for the beam and the slab was given. Okay, that is 35 kilonewton per mm square. It was given, correct? In this problem, where is it? That data. Cable having 33. Yeah, here it is given, correct? Here it is given 35 kilonewton per mm square was the given data for both the precast and in situ cast elements. Precast and in situ cast in situ elements means for beam and the slab it was same, but in this problem, okay, but in this problem it is different. The modulus of elasticity of the beam and the slab are different. For beam it is 35, for slab it is 28 kilonewton per mm square. Mm square, it is not meter square, mm square. Therefore, what will be the procedure? Let us see. For the if different modulus of elasticity is given in the problem, first you need to find the ratio of Young's modulus of modulus of elasticity of the beam to that of slab. Okay, first you find that. First you find the ratio of modulus of elasticity to of beam to that of slab. Let me solve the problem. Solution. Okay, if different Young's modulus is given, then you find ratio of modulus of elasticity alpha, which is equal to EC of beam to that of Young's modulus of concrete of slab. Okay, so for beam it is given as 35, for slab it is given as 28. If you calculate the ratio, you will get 1.25 as the ratio. Okay. See, if the Young's modulus of beam and the slab are different, then finding the moment of inertia is different. Okay, let us find that moment of inertia. It is a T beam. Write the figure of the T beam. The width of the slab given is 400 and depth is 40 mm. Whatever the data was there for the previous problem, same data. Okay, same data. You can see. Here I will show the same data. Okay, 200 mm deep and 100 mm wide. This is for beam, and slab is 400 mm wide and 40 mm thick. Same dimensions I am writing here. 40 mm thick, and depth of beam is 200, width of beam is 100. Okay, for this we need to locate the centroid. We need to locate the centroid. Let G be the centroid of the T section. Okay, let G be the centroid of the T section. First you find the centroid. Let us find centroid first. For that we have the formula. There are two rectangular elements. Therefore, centroid becomes what? A1 y1 plus A2 y2 divided by A1 plus A2. Okay. We will find centroid with respect to the bottom fiber. Okay. We will find centroid with respect to the bottom fiber. Therefore, A1 becomes equal to A1 means if you assume this has component 1, this has component 2. So, area of this flange portion becomes 400 into 40. It is 16,000 mm square, correct? And y1, okay, we are finding centroid with respect to the bottom fiber. Okay, with respect to the bottom fiber, distance of centroid of flange from the bottom fiber, how much it is? It is 200 plus 40 divided by 2. 200 plus 40 divided by 2. What is the answer you get? 220 mm. Okay. Then A2 means area of this beam or rib is equal to 100 into 200. So it is 20,000 mm square. Then what about Y2? Y2 is half of depth, that is 200 by 2. We will get 100 mm. Okay. Y2 will be equal to 100 mm. You can find the centroid now. Tell me the answer. So before that, before calculating, very important, I'll tell you, A1Y1 is equal to 16,000 into 220 plus A2Y2 20,000 into 100, okay, into, okay, into 1.25 into 1.25. You need to multiply. What is this 1.25? It is the ratio of Young's modulus of beam to that of Young's modulus of it is the ratio of modulus of elasticity of the concrete of the beam to that of modulus of elasticity of the concrete of the slab. Okay, therefore for slab no issues. Okay, for beam, EC beam equal to what? 1.25 times of EC slab. That is why while substituting the values for slab, you need to multiply by 1.25. This is important, remember. See, when different modulus of elasticity is given, you need to multiply the ratio of Young's modulus of concrete of the beam to that of Young's modulus of concrete of the slab. Okay, this is only the important step. Okay, whole divided by again 16,000 is the area plus A2 is 20,000 into 1.25 again 20,000 into 1.25. Because of different modulus of elasticities, we need to compensate, we need to balance the cell elastic moduli by multiplying the ratio. Okay, that is why we are multiplying here. So therefore, what is the answer? Y bar is equal to, students, what is the answer? Tell me the answer, please. Tell me the answer, any one of you? Darshita. Kruti, tell me the answer. Any one of you tell me the answer, please. Sumit Kumar. Yes. Tell me the answer, students.
146.82, sir.
Yes. How much?
146.82.
Yes. 146.82 mm. This is from bottom fiber, from soffit. Okay. That is YB, we'll call it as YB, means distance from base of the section, 146.82 mm. Okay. From the soffit means YB, I denoted it as YB, which is nothing but the distance from base of the section. If you want to find distance from here, you mentioned that distance from the base, it is 146.82. 146.82. This is YB. If you want to find from the top fiber, that is YT, you can find it overall depth minus that 146.82. If you do, you will get the distance from top fiber. YT will be equal to overall distance is 40 plus 200 minus 146.82. How much will get? Tell me.
93.18, sir.
93.18 mm. Okay, you mentioned this distance also in the figure. Yt is equal to 93.18 mm. Okay, from top fiber. This is from bottom fiber. Okay, now we have located the distance of the centroid. You can find moment of inertia now. Okay, you can find moment of inertia now. Therefore, moment of inertia, write the side line as moment of inertia. We have the formula for finding the moment of inertia. That is I is equal to BDQ by 12 plus AH square is the formula. AH square is the formula. Now A1, A2, H1, H2 you find. Okay, with corresponding to the rectangle 1 and the rectangle 2. A1 is equal to, we have already determined 16,000 mm square. 16,000 mm square. Then A2 is equal to 20,000. Yes, it is 20,000 mm square. Then H1 and H2 you find. H1 and H2 you find. What is H1? Corresponding to the rectangle 1. Distance of centroid of rectangle 1 G1 to that of centroid of the whole figure. How much it will be? From top fiber, distance of centroid of whole figure is 93.18 minus this 20. If you do, you will get distance between these two centers, G1 and the G. So it is 93.18 minus 40 divided by 2. 93.18 minus 40 divided by 2. So it becomes 20. Answer will be 73.18 mm. Similarly, you find H2 means distance of centroid of rectangle 2 component 2 G2 to the top centroid of the whole figure. Centroid of the whole figure. Okay. So from bottom fiber, distance of centroid of whole figure is 146.82 mm. Okay. And distance of centroid of the rectangle 2 is at a distance of 100 mm. So 146.82 minus this 100 will give distance between G2 and the G. Okay. Therefore it is 146.82 146.82 minus 100 or 200 divided by 2. Tell me the answer. It will be 46.82, correct. 46.82 mm. Okay. Now you can find moment of inertia. Therefore, I is equal to BD cube divided by 12 for the rectangle one. B is 400 into 40 cube divided by 12 plus AH square. A is 16,000 into H1 square is 73.18 square plus for rectangle 2 B is 100 mm, depth is 200 cube divided by 12, okay, plus AH square. A is 20,000 into H square is H2 square 46.82 square into, very important, again you need to multiply by that ratio 1.25. Important, remember, when different elastic moduli are given, you need to balance by multiplying the ratio. Okay, tell me the answer now. I is equal to how much you'll get? Tell me the answer, students.
Sir, 2.09 into 10 power 9, sir.
2.09, huh?
Yes, sir.
Here I got a slight different answer. 2.26 I got. Can you calculate once again?
Yes, sir.
Others, you also calculate, please. Here I got 226 into 10 power 6 answer. 226 into 10 power 6 mm4.
Sir, I'm getting same answer, sir.
Same answer you're getting. Okay,
Yes,
let
sir.
me check the calculation once again. Oh, sorry, here. Sorry. Okay, we have to multiply this 1.25 to this whole term for this AH square. What we have done is, that is why we are getting different answer. Okay, for this whole term you have to multiply. Okay, what we have done is we have multiplied only for this second term. Okay, for full AH square if you have to multiply. Now I think you will get the answer. Check it now.
Sir, 225.9 into 10 power 6,
Yes,
sir.
yes. Now it's correct. Round it up to 226 into 10 power 6 mm. Okay. So like this, centroid and moment of inertia has to be calculated by considering the ratio of Young's modulus of beam to that of slab. Okay. Here we need to multiply 1.25 at numerator and denominator with respect to the beam calculations. Here also with respect to the beam calculation for AH square term we need to multiply. Remember this. Okay. Now we can calculate the deflection, total deflection. Before calculating the deflection, we need to calculate deflection due to the dead load, deflection due to the weight of the slab on the beam, deflection to the pre-stress, and deflection due to the live load. Okay, knowing all the deflections, we can calculate the total deflection. First one for propped construction, right? Case A, for propped construction, for propped construction, okay. For propped construction, deflection due to dead load. First one, deflection due to self weight. Deflection due to self weight of beam. Okay, deflection due to self weight of the beam. Let me go to the previous problem. Okay, this is the problem. Okay, we are solving this same problem only with, but Young's modulus are different. Okay, for unpropped construction, we have calculated the deflection due to dead load of the beam, where moment of inertia corresponding to the beam was taken. Okay, moment of inertia corresponding to the beam was taken. Here, how much it is? I for precast section, how much it is? 667 into 10 power 5 mm square. Okay, but moment of inertia of the composite section, it was given as 1948 into 10 power 5 mm raised to 4. This is the case where both the Young's modulus are same. Okay, for composite section. As the Young's modulus values are given are different, we have calculated the Young's modulus by using that ratio. With that, we got it as 226 into 10 power 6. Okay, but with respect to the beam element alone, this Young's modulus, this moment of inertia remains the same. Okay, with respect to the individual beam element, this moment of inertia remains the same, that is 667 into 10 power 5 mm raised to 4. This remains the same. With respect to the composite section, okay, with respect to the composite section, moment of inertia will be different. That we have calculated just now for the problem. Okay, now deflection due to the dead load of the beam, we have calculated. Moment of inertia is same only, so the answer will be same. Okay, whatever the deflection due to dead load of the beam for you got for this problem, same deflection you get, because this moment of inertia is also same, dead load is same, everything is same. Okay, dead load of the beam is self weight of the beam is same, everything is same, you will get the same answer. Then deflection of a precast beam due to self weight of the slab. Here also, what is the moment of inertia we utilized? We utilized 667 into 10 power 5. Means moment of inertia of the beam only we have utilized. So this answer also same. This step is also same. Okay, this step is also same. Then precessing deflection due to precessing force. Okay, deflection due to precessing force while calculating, here also we have utilized moment of inertia of beam only. This also remains the same. Okay, this value also remains the same. Only the change is here while calculating deflection due to live load. Okay, deflection due to live load, moment of inertia of composite section we have utilized. Okay, here it is 1948 into 10 power 5 mm raised to 4, but in the next problem whatever we are solving, it is 226 into 10 power 5 mm raised to 4. Therefore, up to here the procedure is same, calculation is same. B 8th semester. Okay, up to here the procedure is same, only the calculation is different at this step, deflection due to live load. Okay, what I will do, I will copy the same answers. I am not going to repeat the calculation once again. Deflection due to dead load is 1.67, deflection due to slab weight on the beam is 1.34. okay, deflection due to precious is 5.67. Wherever you have used, okay, moment of inertia of beam alone, there you will get the same answer. Wherever you are using moment of inertia of the composite section, then only the calculation will changes. Okay, these values remains the same, only this moment of inertia value changes. It becomes 226.10 power 6. Is that clear for you all students? Is that clear? You have any doubts? Any doubts? Okay, if you need any clarification, you can ask. I will copy the same answers now. 1.67 mm. Okay. Second step, deflection of precast beam due to self weight of cast in situ slab. Okay, this also remains the same, that is delta SL is equal to 1.34 mm. The answers are similar to the answers of previous problem only. You can write a note as refer previous problem. Okay. Okay, and deflection due to pre-stress or pre-stressing force. Pre-stressing force delta PS is equal to the same value, that is minus 5.67 mm. Okay, only the change is in the last step, fourth step. Okay, that is deflection due to live load. Deflection due to live load. Okay, therefore delta live load is equal to 5 by 384, okay, into WQ L raised to 4 divided by EC into IX. EC into IX. Therefore, delta live load is equal to 5 by 384 into live load on the beam is given in the problem. It is given as 3.2. Okay, in the problem it is given 3.2 Newton per mm into length of the beam is given as 5 meter, that is 5000 raised to 4 divided by EC into IX. EC Young's modulus of beam you will substitute, or Young's modulus of slab you will substitute here? Which one has to be substituted here? Here we need to substitute Young's modulus of concrete of beam, that is 28. Okay. EC of beam. Okay. Because what we have done is, while calculating this moment of inertia, while calculating the moment of inertia, we have compensated or we have balanced this Young's modulus of we have balanced this moment of inertia of a beam by multiplying with that ratio 1.25. That is why we have to substitute Young's modulus of concrete of beam only. Okay, and IX will be 226. Okay, not the 1948. 226 into 10 power 6. By this we get deflection due to live load. Tell me the answer.
4115.30, sir.
411. Here you need to make the conversion here before that. Right? This is mm square. Okay, you change this. This is mm square. EC of slab or beam is equal to 35 kilonewton per mm square, equal to 35 into 10 power 3 Newton per mm square. EC of slab is equal to 28 kilonewton per mm square, is equal to 28 into 10 power 3 Newton per mm square. So here it is 28 into 10 power 3. Divided by 10 power 3, you do wallet answer. What is the value? I think
4.11.
yes, 4.11 mm. Okay, 4.11 mm. Now you can calculate the total deflection. Therefore, the total deflection will be delta is equal to deflection due to dead load of the beam, deflection due to slab load on the beam, plus deflection due to precessing force, plus deflection due to lie load. Deflection due to dead load is 1.67 plus 1.34 minus 5.67. 1.67 plus 1.34 minus 5.67. Deflection due to lie load is 4.11. What is the final deflection?
One 1.45.
Yes, 1.45 mm. Okay, so this is the calculation of deflection for propped construction. There is one more case, we need to calculate deflection for unpropped construction B. So now we have calculated for unpropped construction. Sorry, unpropped construction. Now for propped construction calculation, deflection for propped construction. Okay, deflection for propped construction. So while finding deflection for propped construction, I'll go to the previous problem. See, while calculating the deflection for propped construction, while calculating deflection due to slab load on the beam, we have taken moment of inertia of the full section, moment of inertia of the composite section. Okay, for unpropped construction, we have taken moment of inertia of only the beam 667. But for propped construction, when calculating the deflection due to the slab load on the beam, you need to take moment of inertia of the composite section, because it will act as a whole, it will act as a monolithic section, that is why. Okay, here it is 1948 into 10 power 5, but in this problem it is 226 into 10 power 6. Okay, 226 into 10 power 6, and you need to take Young's models of concrete below, right? In case of propped construction, the beam and slab is considered as a composite section. Okay, means such a moment of inertia of the T section has to be taken. Therefore, deflection due to slab load on the beam is equal to 5 by 384 into WSL L raised to 4 whole divided by EC into I composite. Okay, is equal to 5 by 384 into 0.384 is the slab weight given. It is given directly in the problem. .384 weight of cast in situ slab 0.384 it is given. Same way I am taking 0.384 into length is 5000 raised to 4 whole divided by, here also Young's modulus of concrete of the slab, that is 28 into 10 power 3. Into I composite. For this I composite we have calculated as 226 into 10 power 6. Therefore it is 226 into 10 power 6. So what is the deflection due to slab load on the beam?
0.493, sir.
0.49 3 mm. Okay. Now we can calculate the total deflection. Therefore, total deflection delta is equal to deflection due to dead load plus deflection due to slab load plus deflection due to restressing force plus deflection due to fly load. Deflection due to dead load is same value is 1.67 plus 1.34, 1.67 plus 1.34 plus 0.493 for proper construction. 0.493 0.493. Then deflection due to pre-stress is minus, right? Minus 5.67. Minus 5.67 plus deflection due to live load, it is 4.11. 4.11. Therefore, the total deflection delta is equal to how much?
0.603, sir.
Is 0.603 mm. Okay, this completes the problem. The procedure is 90% similar to that of the problem which has same Young's modulus, but wherever the moment of inertia of the composite section is used, no, there you need to substitute the moment of inertia of the composite section with different elastic moduli that we have calculated earlier. Okay. Okay, next is flexural strength of the composite section. Write this problem. This is the last problem of this model, fifth model. We will solve this as well. Write the problem. Done? Read the figure. Read figure also. Okay. So finding the flexural strength, it is 100% similar to that of finding the flexural strength of the normal PSA beam. Whatever the procedure we have followed for in model 3, no, same procedure here. We will solve this example now. The cross section of a composite beam is of T section having pre-tensioned rib 80 mm wide and 240 mm deep. Okay. The beam dimensions are given, and cast in situ slab of 350 mm wide, 350 mm wide, and 80 mm thick. The thickness of the slab is also given, that is written in the figure. The pre-tension beam is reinforced with 8 wires of 5 mm diameter with an ultimate tensile strength of 1600 Newton per mm square. 8 number of wires with FP is equal to 1600 Newton per mm square. Located 60 mm from the soffit of the beam. They are located at 60 mm from the soffit of the beam. See, overall depth it is given, means depth of flange is given, depth of rib is given. Including adding both, you will get total depth minus this cover will give effective depth. That I have calculated as 260 mm. Okay, the compressive strength of the concrete in cast in situ cast and precast element is 20 and 40 Newton per mm square. Compressive strengths are given. If adequate reinforcement are provided to prevent the shear failure at the interface, estimate the flexural strength of the composite section. We need to estimate flexural strength of the composite section. Okay, you write all the given data first. So all the geometric properties are written in the figure itself. Here number of bars given is 8 number of bars having 5 mm diameter. Calculate the area pre-stressing steel. AP is equal to pi d square by 4, pi into 5 square by 4 into 8 numbers. This is number of wires. Number of wires. What is the area, total area you get? Area pre-stressing steel. How much?
157.07.
157, correct. 157 mm square. Okay. So here the Young's modulus values, modulus of elasticity values are given. C2 means for slab it is 20 and for precast element for beam it is 40. That you write below. FCK for slab. FCK for slab, that is flange. FCK of flange is equal to 20 Newton per mm square, and FCK for beam, nothing but web, that is FCK of web is equal to 40 Newton per mm square, and effective depth you can calculate. Effective depth, it is already calculated in the figure. Let me write it once again. Total depth is 80 plus 240 minus 60. 80 plus 240 minus 60, if you do, you will get effective depth, that is 260 mm. That is the effective depth. Now we need to calculate flexural strength of the flange section. Okay, for flange section, first we need to assume neutral axis either it lies in the flange or it lies in the web. Okay, what we will do, assume neutral axis lies within the flange. We will assume that neutral axis lies within the flange because the depth of the beam it is little bit less here. That is why when depth of the beam is less, then most of the times the neutral axis fall within the flange only. That is why what we will do in the step 1, assume neutral axis lies within flange. Okay, that is XU less than DF we will assume first. Okay, for that we will check whether it lies within the flange or not. For that I will go to the code book. Okay, we have table number 11. It is a pre-tensioned beam. First you calculate this ratio AP FP divided by BD FCK. You calculate AP FP from table 11, from table 11, page number 59. Let me check. Yes, 59. Page number 59. 59. IS 1343 1980. The APFP divided by BDFCK is equal to APFP divided by B means width of flange. Okay, we have assumed it lies within the flange into D into FCK of what? Flange again. Okay, because we have assumed depth of neutral axis lies within the flange. That is why AP is equal to FP value is given, it is 1600. Okay, in the given data you can write FP is equal to 1600 Newton per mm square, ultimate tensile strength. AP we have calculated, it is 157. 157 into FP is 1600 divided by width of flange is 400. It is 350 mm. And effective depth is 260. 350 into 260 is the effective depth into FCK of flange is 20 mm, 20 Newton per mm square into 20. So what is the ratio then?
0.138.
0.138 means you can round it off to 0.14. Okay. Now corresponding to APFP divided by BDFCK is equal to 0.14. You calculate XU by D value for pre-tensioning case. Okay. For 0.10 it is 0.217. For 0.15 it is 0.326. For 0.14 you calculate. Do the interpolation. Tell me the answer. XU by D value. From table 11. From table 11. For pre-tensioned case. In the problem it is said that it is pre-tensioned beam. Pre-tensioned for APFP divided by BDFCK is equal to 0.10. Corresponding XU by D was how much it was? 0.217. We need for 0.14 value XU by D is equal to, we need the answer. For 0.15 also we know the answer. XU by D value we know how much it is, 0.326. Do the interpolation. By interpolation, XU by D is equal to, tell me the answer. Yes. XU by D is equal to, do the interpolation.
Zero 0.304, sir.
Yes, 0.304. Okay. Now you can calculate the depth of neutral axis. Effective depth is known, XU by effective depth is 260 is equal to 0.217. 304. By this you will get the depth of neutral axis. How much?
$79.
79 mm. Okay, this is the depth of neutral axis, 79 mm. You just check the depth of flange. Depth of flange is 80 mm, but depth of neutral axis lies at a distance of 79 mm from top fiber. Therefore, depth of neutral axis lies within the flange. Our assumption is correct. Okay, here you can write which is less than 80 mm. That is depth of flange. Hence neutral axis lies within flange. Our assumption is correct. Assumption is correct. Okay. Now you can calculate moment of resistance. Moment of resistance. To calculate the moment of resistance, we have the formula M is equal to FPU AP into D minus 0.42 XU. D is known. Depth of neutral axis XU is known 79. AP is known. FPU you need to calculate. FPU you can calculate using same table number 11 only. Madam. Okay, madam. ಹೌದಾ ಓಕೆ ಓಕೆ you first calculate FPU by 0.87 FP. Okay, a value by referring this table. We have already calculated this ratio, correct? Okay. Now to calculate FPU from table 11, from table 11, okay, AS1343 1980. You can calculate AP by AP, AP for AP FP divided by BDFCK. What is the ratio we got? We got this ratio as 0.14. 0.14 corresponding. Okay, corresponding. What is this? FPU by 0.87 FP. Corresponding FPU divided by 0.87 FP is equal to, just for the table we need for 0.14, for 0.110 it is 1, 0.15 it is 1, obviously for 0.14 it will be 1 only, therefore FPU divided by 0.87 FP is nothing but ultimate tensile strength, that is given. How much it is given? It is given as 1600 Newton per mm square. Therefore it is 1600 is equal to 1. By this you will get FPU.
sir.
1392 Newton per mm square. Okay. Now you can calculate moment of resistance using this formula. Every parameters are known. Therefore, the moment of resistance is equal to Therefore, moment of resistance is equal to, the formula is FPU into FP into D minus 0.42 XU. FPU, ultimate moment of resistance, is equal to FPU into FP into D minus 0.42 XU, which is given in page number 59 IS 1343. Okay, therefore mu is equal to FPU is 1392 into FP value is 1600 into D minus 0.42 XU. D is effective depth. How much it was effective depth? 260.
ಅದು AP ಅಲ್ಲ ಸರ್?
Yes.
ಅದು FP ನೋಟ್ಸ್ ಅಲ್ಲಿ AP ಅಂತ ಕೊಟ್ಟಿದ್ರಿ ಸರ್ ನೀವು.
AP. Okay. Just a minute. I'll check with AP only. AP only it is. I'll change it now. AP only. So while writing the mistake has happened. Okay, AP only. AP into AP into D minus 0.42 XU. Okay, FPU into AP. Okay, area of pre-stressing steel, it is 157 into 157 into D minus 0.42 XU. D is 260 minus 0.42 into XU. Depth of the neutral axis, we got it as how much? 79 mm into 79. So by this we will get moment of resistance.
$49.57 10 power 6.
Okay, 49.57 into 10 power 6 Newton millimeter, or mu is equal to 49.57 kilonewton meter. Okay, so to this, the all problems of model 5 is over. Okay, full syllabus of the model 5 is completed, and full syllabus of the subject also completed, students. Okay, to this I think my part is over. Okay, next is your part. Okay, whatever the things to be done from my side, I have done all the things. Okay, I have solved all the problems. Okay, I have given all the course materials. Okay, each and every notes of each model I have shared. Okay, now your part. Okay, you need to put your effort. Okay, you need to gain the knowledge, and you have to perform well in your external examination. Okay, see, this model 5 is it is mix of model 2, model 1, 2 and model 3. Okay, in model 1 you have learnt analysis of stresses. Okay, analysis of stresses. Okay, in model 2 you have learnt how to find the deflection of the beam. In model 3 you learned how to find the flexural strength of the beam. Okay, if you prepare, if you are thorough with model 1, 2 and 3, then model 5 it is very easy. Okay, some minor changes are some minor changes will come that you can incorporate, just referring to the notes. Okay, but this model 5, no, it is newly introduced in your 17 scheme syllabus. You are the first batch for 17 scheme. Don't know what may be the type of question they are going to ask in the examination. So my suggestion is model 5 you can attempt. If you prepare for model 1, 2 and 3, you can attempt, no problem. But my suggestion is to go for model 1 to 4 you read. Okay, you prepare for model 1 to 4. Model 5 just have a look on model 5. Okay, if you have sufficient time, you thoroughly study all the models, that is well and good. It's very good if you study all the 5 models. If you are lagging with the time, then my suggestion is to go for model 1 to 4. If you prepare for model 1 to 4, you can just have a look on model 5. You just keep in mind where are all the changes in the calculations will come. You can directly solve the problems of model 5, even if it is asked in the examination. Okay. So tomorrow also I have one class. There I will try to revise. I'll just glance all the models. Okay, in the tomorrow's class. Do you need any clarifications with respect to subject, students? Students, with respect to the subject, do you need any help or any inputs from my side? I will be ready. Okay, it's very easy subject. See this Psc subject, no? If you understand the concept properly, okay, if you understand the concept properly, you will get out of out marks in this subject. Okay, understanding the concept is very important and you should be perfect in doing the calculations. You should not commit any mistakes in doing the calculations. Understanding the concept is very important. Okay. So prepare well for your examinations. Okay. I'll take the attendance.